Okay, I want to give you a little sense of why L'Hopital's rule works. So let's take, for example, this problem of e to the x squared minus 1 over 5x squared. And if we plug 0 in, we get 0 over 0 in indeterminate form. That also means that if you're actually trying to do something, graphically, we end up with a hole at that spot. It's not really a graph there, but of course, our graph's not very good at knowing that, so it's always a little bit misleading. Okay, so it looks like it crosses there. It doesn't, but the limit does exist, and I want to show you, using L'Hopital's rule, why something like that might work. So we have a situation, this indeterminate form. The limit as x approaches some value a of f of x over g of x, where if you just try to plug in the value a for numerator and denominator, you get 0 and 0. Yeah. So L'Hopital's rule tells us that, hey, we can do that limit. It's equivalent to the limit of the derivative of the numerator and the derivative of the denominator. Please don't get L'Hopital's rule mixed up with quotient rule. A few people do. Careful of that. I like to always write, when I use L'Hopital's rule, I like writing this little symbol, L apostrophe H, to remind me that that's what happened. Otherwise, people can get a little confused looking over work. So in showing why this could work, let me just do it in one specific case, as I said, where we have this indeterminate form of 0 over 0. But also, I'm going to make the assumption that the derivatives themselves, f prime of a and g prime of a, are both not 0. So in other words, when I use L'Hopital's rule right away with one step, then I'll be able to plug in a, and I won't get 0 over 0. Okay, so just for this example. And what we want to think about is this idea of linear approximation. Because the linear approximation, remember, it says that we can approximate a function f of x as, this is the tangent line approximation, and where is this good? Well, it's not good everywhere, right? It's good just for values, of course, near x equals a. Anywhere else, you get too far away from a and you get very far off. But after all, we are going to be talking about a limit as we're approaching a, right? So we're getting really, really close to a. And so if you're thinking about zooming in on the graph of this sort of thing, of course, a tangent line is going to be a very, very good approximation, okay, for both numerator and denominator. Think of them as separate functions, okay? So if we think about trying to take this limit, f of x over g of x, because we're getting really close to a, the tangent lines are going to give you exactly the same result. No difference. So even though it's an approximation, in the limiting case, they're identical. Now, because we're saying, we made this assumption that f of a was 0 and g of a was 0. Remember, I'm just assuming that, I'm sorry, not assuming that, that was given to us. And so at this point, we can say, look, even our tangent line approximations, f of a is 0, g of a is 0. So if that's the case, we can, of course, just drop those out. And now we have f prime of a times x minus a and g prime of a times x minus a. And that's in the top and bottom. And, we still can't plug a in because you do that, you get 0 over 0. However, before we plug a in, you can say, look, we just have x minus a on top and bottom. We can cancel those. And in the limiting case, they're going to be identical. Because again, we're not at a, we're getting close to a. That's why they cancel. Well, if you do that, we have just f prime of a over g prime of a. And that's exactly what we said needs to have happen in L'Hopital's rule. But this gives you a sense of why L'Hopital's rule works, at least for this specific case where we made the assumption you only had to take the derivative once. Now, you've seen that L'Hopital's rule, sometimes you take the derivative once and you still are in the indeterminate form of 0 over 0 kind of thing, and you have to use L'Hopital's rule a second time, a third time, maybe a few times. But the argument is similar. It's just we have to go a little more complicated than tangent line approximations. But that's something a little beyond what we're able to do right now, and it could be proven in Calc 2. But for now, tangent line gives you a sense of why L'Hopital's rule works. L'Hopital's rule, and as I said, I like to write this notation to indicate that's what we're doing. Keep in mind we have to keep writing limits as well each time. So derivative of the numerator, so derivative of an exponential is the exponential times, using the chain rule, derivative of the exponent, so derivative of x squared is 2x, and minus the derivative of 1, which is 0, divided by derivative of 5x squared is 10x. And if we try to plug 0 in here, it doesn't work, but it's always smart to simplify things first, right? Because you can cancel out these x's, and now it's a straightforward plug in the numbers. Now it works. So we get e to the 0 times 2 over 10, and of course e to the 0 is 1, so we get 2/10 or 1/5. Let's take a look at another one, sort of a cautionary tale on this one. This one, using L'Hopital's rule, so we'll take the limit as x goes to pi over 4, and I'm just going to indicate we're using L'Hopital's rule. So derivative of the top is 2x, and the derivative of the denominator, tangent, would be secant squared x. And now as we go and plug in, pi over 4, I guess if we're plugging it in we don't need to write that, so we'll have 2 times pi over 4 on top, and in the denominator we'll have secant squared of pi over 4. And so who remembers the secant of pi over 4? I suspect a lot of you don't. So instead, let's remember that, a secant is really 1 over cosine. So what we can do is we can rewrite this as a cosine squared in the numerator of pi over 4. Okay? And so we'll have 2 times pi over 4 would be pi over 2 simplified. And then cosine of pi over 4 is square root of 2 over 2. And that gets squared. And squaring that is going to be 2 over 4. So we have pi over 4 times 2 over 4 for a grand total of, well, a little simplifying, that's a half pi over 8. Okay. The problem is that limit is actually not pi over 8. Why not? What did we do wrong? Well, what we did wrong, I intentionally was doing this with the danger that L'Hopital's rule doesn't work here. Okay? So L'Hopital does not apply. But why not? The reason L'Hopital's rule doesn't work is the fact that in this original thing, I didn't bother to see if I had an indeterminate form. And I did that on purpose because it's a very common thing that people do, is you end up liking L'Hopital so much that you try to use it even when it doesn't work. Okay? So just sort of going back out here and saying, well, wait a minute. I could just have started by plugging in the numbers right away. I can plug pi over 4 into the numerator, get pi over 4 squared. Pi over 4 squared. And the denominator, we have tangent of pi over 4. So the numerator is pi squared over 16. The denominator, tangent of pi over 4, that's just 1. So the answer is pi squared over 16, not the goofy answer of pi over 8 that we got here. Okay, so if you use L'Hopital's rule when it doesn't apply, you get a wrong answer, and you don't really want to do that. So first, make sure L'Hopital's rule apply. There's a cautionary tale here, in a sense. And I'd like to take a look at the limit as x approaches 0 from above of x to the x. Now, why am I only doing a one-sided limit? Well, this function does not actually exist for negative values of x, because we can't take a negative value of x to a negative power in all cases. That only works for sort of these odd powers. But if we're talking about real values, it only works on one side. So be aware that this is only defined for positive values. And, what do we mean? How do we even plug 0 in? Because you think of 0 to any power, I think you've kind of been trained. 0 to any power, anything at all, 0. And you're used to saying anything to the 0 power is 1. So which is it? Is it the 0 or is it the 1? Because it's trying to do both at once. Okay? And looking at the graph, it certainly appears to be approaching the value of 1. But we want to show that, in fact, it works. Now, it doesn't look like L'Hopital's rule applies here. And it doesn't yet because it's not in one of those indeterminate forms. But what we can do is we can rewrite this. And I'm going to rewrite this as, we're going to write y as x to the x. And now I'm going to take the log of both sides. Very much like log differentiation. Okay, so by doing that, I can then take this x and write it down front. All right, and even if we're saying, okay, if I'm going to take the limit of this thing, the natural log of 0 is undefined. Okay, but as we approach 0, natural log is going to negative infinity. Hopefully you're good with your natural log function. Looks like that with that vertical asymptote here. So it's approaching negative infinity, in other words, getting really big negative, and that's going to 0. So it's not of a L'Hopital form if we've got this kind of thing going to 0 and this part is going to negative infinity. Okay? So what we're going to have to do is rewrite. And a way we can rewrite this is the natural log of x divided by 1 over x. Kind of a goofy form, but now we're going to take the limit as x approaches 0 from the positive side of the natural log of x divided by 1 over x. Now, in that particular limit, as x is getting really small, we said that that numerator piece is going negative infinity. The denominator, as x goes to 0, 1 over x is getting really big and just on the positive side. So we have this indeterminate form of negative infinity over infinity. So we're allowed to use L'Hopital's rule and have the limit as x approaches 0 from above. The derivative of natural log of x is 1 over x. And the derivative of 1 over x is negative 1 over x squared. And maybe you have to think of 1 over x as x to the minus 1 and use the power rule. Now let's just do a little rewrite. Instead of dividing by this negative 1 over x squared, let's instead multiply by its reciprocal, which would be negative x squared over 1. And by writing it that way, we can see, well, this x will cancel with one of these x's, leaving us with a negative x, actually just a negative x. And so now as x goes to 0, this whole thing's going to 0. Now, we're not done yet. Remember that in the original problem, this was x to the x, but I took the natural log of this. So really what I found is not this limit, I found the natural log of the limit. Well, how do we undo that? Well, we undo a natural log by taking e to the power, right? So really, we're saying this is the same as the limit as x approaches 0 from above of e to the natural log of x to the x. And this numerator, that's the limit we just found to be 0. And so we now have e to the 0, which is 1. Kind of a tricky example. Again, like logarithmic differentiation, only with limits instead.